Okay, the third question is how do we know our model, our ant model, is actually valid? How do we validate this ant model? Basically, we need to use complex pattern to validate it because the purpose of this agent-based modeling is trying to use simple rules to help us to capture the complex real world. So if we can with this model, simulate very complex patterns, it actually validates our model. Previously, we know there is a complex pattern. We hope our model can simulate. That is, given two pile of food, same distance, same amount. Our model should simulate that the ant colony as a whole will take on one pile of food first and then take on the other. It should not take on two food at the same time, or at least it should devote most of this capacity to one pile of food and then to another, not equal efforts at the same time. Suppose this is what um, the biologists believe, and this is what's the real world, how the real world behaves. Then our model should be able to reproduce this phenomenon, just like this one. Okay, gets one pile first, and then another pile, and then the last pile. Okay, although so far it looks fine. It gets one pile first, and then the second pile, and then the furthest pile. But sometimes it does not work that well. Okay, this one works okay. Okay, fine. But sometimes it does not work as we wish. So far it's all worked fine. Fine. Okay. But sometimes they may really try to get two piles at the same time. But so far everything works okay. So far it just finish one pile first, another, and then the last one. Okay, just now we see that these two piles almost finish at the first time, at the same time, but one pile slightly faster. Okay, so far it seems that our model is able to reproduce the very complex phenomena suggested by the biologist. Therefore, we say this complex phenomenon pattern validates our model. Okay, so that's also another way we can try to use to validate our model. That is, we say if our model is able to reproduce complex pattern. The reason why we say it's complex is because in this case, the ants colony as a whole, it can do much more difficult and complex things than single ants multiply itself. Multiply its effects. For example, um, we can try to experiment 100 times for 1,000 ticks each time, and then to calculate how much food can a single ant gather on its own. And then we take the average. For example, with 100 simulation, every simulation for 1,000 ticks for a single ant, then take an average. That single ant can get 3.71 food on average in any simulation. So if we consider the whole of that ant colony is simply the multiplication of that single ant, then we can multiply 100 to form that 100 ant colony. And that 100 ant colony should be able to get 371 food on average. So that is the assumption. But if we are able to simulate the real ants colony, then 100 ants as a colony should get much more food than the previous experiments. So will this whole ant colony together get more food? We don't know. We have to experiment it. So we tried 3 groups of experiments. Here is experiment A, which is simply to multiply itself. Experiment B treats it as a whole. And we do these 2 experiments 100 times each. And we set the parameters to be 88 for diffusion, 6 for evaporation. And we find out that their difference, the 2 group difference, is about 6% of it's about 6% of 371 compared to A experiment. But when we try different parameters, say parameters evaporation from 6 to 3, the difference becomes a lot larger, from 6% to 17%. And if we change in diffuse from 88 to 60, we still get a very big difference. So it suggests that if we set the parameters right, our model may be able to create an ant colony actually as a whole can perform much more complex, can do much more efficient work. In this case, more efficiently get the food than one single ant multiply itself 100 times. So if this number is significant, then we can say our model is able to produce complexity of ant colony rather than just multiply itself. So we did capture something real complex.